Tonight, we begin with two machines that were never meant to become legends. Two quiet spacecraft built in the language of the 1970s, launched before smartphones, before home internet, before most people had ever touched a personal computer, and yet somehow sent into a darkness so large that even now, after almost half a century of flight, they are still only at the beginning of the space between the stars. Before we travel farther, if this journey brings you a little wonder and peace tonight, please like the video, subscribe to the channel, and comment where you're listening from. Voyager 2 left Earth first, rising from Cape Canaveral on August 20th, 1977. And Voyager 1 followed on September 5th, taking a faster path that would let it reach Jupiter and Saturn ahead of its twin. So the numbers in their names do not remember the order of launch, but the order of arrival. A small historical detail that already hints at how carefully these journeys were shaped by geometry, timing, and the patient mathematics of gravity. Their original mission was not to leave the solar system in the grand poetic sense people often imagine today. It was far more practical and in some ways more astonishing, because NASA had noticed a rare alignment of the outer planets, a configuration that occurs only about once every 176 years, where Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a spacecraft could borrow speed from one giant world after another, bending its path with gravity instead of carrying impossible amounts of fuel. This was the heart of the Grand Tour idea. Not a straight road, not a rocket simply pushing harder and harder into the night, but a choreography of falling, turning, and being flung onward, as though the planets themselves had briefly opened a set of doors across the outer solar system. The Voyagers were designed first for close-up studies of Jupiter and Saturn, their rings, moons, magnetic fields, radiation belts, atmospheres, and hidden systems of motion. And the primary mission was expected to last only a few years, long enough to pass those great planets and return measurements no human instrument had ever made from so close. But a spacecraft, when it is built with enough redundancy, enough simplicity, and enough stubborn engineering grace, sometimes becomes more than its design life. Each Voyager carried a large, high-gain antenna, a suite of scientific instruments, 3 radioisotope thermoelectric generators powered by the decay of plutonium-238, and computers so small in memory by modern standards that comparing them to today's devices almost feels unfair, like comparing a candle to a city skyline. Yet those modest systems were built to survive cold, radiation, distance, and time. Their power was never going to last forever. The heat from plutonium decay would slowly fade. The available electrical wattage would decline year after year, and engineers on Earth would eventually have to choose which heaters, instruments, and subsystems to turn off, not because the spacecraft had failed, but because survival at the edge of the sun's domain is a slow negotiation with dwindling energy. That is part of what makes the story so haunting. These machines are not immortal. They are aging. They are being kept alive with careful choices, patient commands, and the extraordinary discipline of people who know that every watt matters when a signal must cross billions of miles before it can even be heard. And yet the Voyagers kept going. They passed Jupiter in 1979, and the solar system stopped being a collection of distant points and became a place with weather, storms, volcanoes, rings, oceans hinted beneath ice, and magnetic environments far stranger than the clean diagrams of textbooks. Voyager 1 flew by Jupiter and Saturn, then was directed onto a path above the plane of the planets, beginning its long outward climb into the dark. Voyager 2, moving more slowly and along a different path, continued the broader tour, visiting Uranus in 1986 and Neptune in 1989, becoming the only spacecraft ever to see those ice giants up close. By any normal measure, the mission had already exceeded history. If the story had ended after Neptune, Voyager would still have been one of humanity's greatest scientific achievements. But the most important discovery for our question tonight did not come from a planet, a moon, a ring, or a storm. It came after the famous worlds had fallen behind, after the cameras had completed their work, after the spacecraft had become tiny moving points in a region where sunlight grows thin and the sun begins to look less like the ruler of the sky and more like one star among many. This is where the Voyager story changes from planetary exploration into something quieter and deeper. Heliophysics at the edge of the solar system. The study of where the sun's influence finally weakens enough for the galaxy to press in. To understand why that matters, we have to be careful with the phrase edge of the solar system, because it can mean different things depending on which physical boundary we are talking about. If we mean the last major planet, then Neptune is a kind of edge. If we mean the realm of icy worlds beyond Neptune, then the Kuiper belt pushes the boundary farther outward. If we mean the distant gravitational family of the Sun, then the hypothetical Oort cloud may extend thousands or even tens of thousands of astronomical units away, so far that Voyager will not reach its inner regions for centuries. But the Voyagers were not detecting the outermost reach of the Sun's gravity. They were approaching a different kind of edge, a plasma boundary, a magnetic boundary, a place defined not by where objects orbit, but by where the solar wind stops being the dominant medium. The Sun is not only a source of light. It continuously releases a stream of charged particles, mostly protons and electrons, flowing outward as plasma and carrying the Sun's magnetic field through interplanetary space. This flow, called the solar wind, expands around the planets and helps create the heliosphere, a vast protective bubble of particles and magnetic fields generated by the Sun. Inside that bubble, the environment is shaped mainly by our star. Outside it, the local interstellar medium begins to dominate, a thin mixture of plasma, neutral atoms, dust, cosmic rays, and magnetic fields belonging not to the Sun alone, but to the wider neighborhood of the Milky Way. Before Voyager reached that region, scientists had models. They had equations from plasma physics, magnetohydrodynamics, shock theory, and solar wind measurements near Earth. They could estimate the pressure of the solar wind pushing outward and the pressure of the interstellar medium pressing inward. They could imagine the heliosphere as a bubble, perhaps stretched somewhat by the Sun's motion through the galaxy, perhaps shaped like a comet with a nose and a tail, but still something that could be sketched, simulated, and predicted. The logic was elegant. A supersonic solar wind should eventually slow down at a termination shock. Beyond that, a turbulent outer layer called the heliosheath should carry heated, compressed solar plasma toward the final boundary. And at the heliopause, the outward influence of the solar wind should give way to interstellar space. In principle, Voyager would measure this transition. Solar particles would decline. Galactic cosmic rays would rise. The magnetic field might shift. Plasma conditions would change. A line that had existed first in mathematics would become a place with data. But the deeper lesson of exploration is that a model is not the territory it describes. A model is a lantern. The universe is the cave. The Voyagers were not sent merely to confirm what scientists already believed. They were sent, in the end, to let reality correct the map. And this is where the quiet suspense begins. Imagine those two spacecraft, each moving outward year after year, their speed impressive by human standards and almost motionless by interstellar standards, crossing one astronomical unit after another while Earth became a radio whisper behind them. Every command from Earth had to travel at light speed across a widening gulf. Every answer took hours to return. The spacecraft did not see a glowing wall ahead. They did not enter a dramatic gate. They simply kept measuring particles, fields, waves, and radiation, while scientists watched for the first signs that the sun's invisible empire was changing shape around them. Voyager 1, farther and faster, would eventually become the first human-made object confirmed to enter interstellar space in 2012. Voyager 2 would follow in 2018, crossing the same kind of boundary from another direction, and giving scientists a second, precious point of comparison. But at the beginning of this chapter, we are not yet at the heliopause. We are standing at the threshold of the story, with the original mission behind us and the greater mystery ahead. Two spacecraft that were expected to study giant planets for a handful of years had become instruments at the edge of the sun's breath. They had outlived their warranty, outlived their first purpose, outlived the world that built them in many ways, and continued into a region where the solar system stops feeling like a familiar arrangement of planets and begins to reveal itself as a moving bubble inside the galaxy. That is why Voyager matters so much. It did not simply travel far. Distance alone is not the deepest achievement. It traveled far enough to test the boundary between what we thought we understood and what the universe was actually doing. And once it reached that boundary, the answers would not be clean, simple, or perfectly obedient to the old models. The edge of the solar system would turn out to be farther, stranger, more dynamic, and more alive with invisible structure than anyone had expected. Before we can understand those discoveries, we must first understand the thing Voyager was flying through all along. The solar wind, the unseen river of charged particles that begins at the sun and flows outward until billions of miles away, it finally meets the dark pressure of the stars. Before Voyager could surprise anyone, scientists first had to imagine what the edge of the solar system should be. And in the quiet decades before those spacecraft reached the darkness beyond Neptune, that imagined edge was built not from photographs, because no camera had ever seen it, but from equations, pressure balances, solar wind measurements near Earth, radio observations of distant gas, and the strange but elegant logic of plasma moving through a galaxy that is almost empty, but never truly empty. To the early architects of heliospheric science, the sun was not only a glowing sphere in the sky, not only the source of daylight and warmth, but a star continuously losing a little of itself into space, releasing a thin stream of charged particles from its outer atmosphere, the corona, where temperatures rise so high that ordinary gas becomes plasma and gravity can no longer hold every particle close. This outflow, the solar wind, had once been controversial when Eugene Parker developed the theory that the corona could not remain static, because a million-degree atmosphere should naturally expand outward, accelerating into interplanetary space as a supersonic flow. And what began as a mathematical claim eventually became a measured reality when spacecraft in the early space age detected the steady stream of protons, electrons, and magnetic fields moving away from the Sun. From that point onward, the solar system could no longer be pictured as a set of planets orbiting in a passive emptiness. It had to be understood as a vast, breathing plasma environment, a place where the Sun extended itself invisibly far beyond its light, carrying its magnetic field outward in spiraling patterns shaped by rotation, expansion, and the motion of charged particles that cannot simply ignore electromagnetic forces. Near Earth, the solar wind can be felt indirectly through geomagnetic storms, auroras, and the pressure it places on planetary magnetospheres. But the question that mattered for Voyager was what happens when that wind travels so far that its strength fades with distance and the galaxy begins to push back. The basic mathematics seemed graceful in its simplicity. The solar wind expands outward, and as it spreads over a larger and larger sphere, its dynamic pressure decreases roughly with the square of distance. So every doubling of distance weakens its outward push by about a factor of 4, while beyond the solar system there is the local interstellar medium, incredibly thin yet still possessing density, thermal pressure, magnetic pressure, and relative motion because the Sun itself is moving through its galactic neighborhood. Even if that interstellar material contains far fewer particles than any vacuum chamber on Earth can easily suggest in ordinary human terms, it is not nothing. And across astronomical scales, almost nothing becomes enough to matter. A few particles, a weak magnetic field, and a faint galactic headwind can stop a star's plasma river when the river has spread thin enough. This was the foundation of the pre-Voyager picture. Somewhere far beyond the planets, the outward pressure of the solar wind would meet the opposing pressure of the local interstellar medium, and where those two influences balanced, the Sun's bubble would end. Scientists called this bubble the heliosphere, and they expected it to be large, perhaps shaped somewhat by the Sun's movement through the Milky Way, perhaps compressed on the forward side and stretched behind into a long tail, but still understandable as a coherent structure with layers. The first major layer in this predicted structure was the termination shock, a name that sounds dramatic enough to resemble an explosion, though in plasma physics it means something more precise and more beautiful. The solar wind, while young and strong, travels faster than the speed at which certain pressure disturbances can move through that plasma. So in a broad sense, it behaves like a supersonic flow. When such a flow meets resistance from an external medium, it cannot adjust smoothly forever. Information cannot travel upstream fast enough to warn the incoming plasma, and a shock forms. At this shock, the solar wind should slow abruptly, heat, compress, and change its magnetic behavior, transforming from a faster, more freely expanding flow into a slower, disturbed outer flow. In the pre-Voyager models, this termination shock was expected to lie tens of astronomical units beyond the Sun, somewhere past the realm of the known outer planets, but still well before the final border with interstellar space. Beyond it, scientists predicted the heliosheath, a thick transitional region where solar material would no longer race outward in a clean supersonic stream, but would instead move more sluggishly, pushed, squeezed, and redirected as it encountered the pressure of the galaxy. The heliosheath was expected to be turbulent because plasma threaded by magnetic fields rarely behaves like a calm pond. It can develop waves, irregularities, instabilities, and complex flows. Yet the dominant material there should still come from the Sun. This was important because the heliosheath was not supposed to be interstellar space itself. It was more like the surf zone before the open ocean, a place where the solar wind had lost its youthful speed but not its identity. Then came the final boundary, the heliopause, the surface where the solar wind could no longer push outward as the dominant force, and the local interstellar medium took control. In the cleanest version of the old picture, crossing the heliopause should produce a recognizable set of changes. Particles associated with the Sun should fall away. Galactic cosmic rays should become more intense. Plasma conditions should reflect the denser interstellar environment, and the magnetic field might rotate toward the direction of the galactic field outside the bubble. It was not unreasonable to expect this. The physics had deep roots. Shock waves were known in gases and plasmas. Pressure balance is one of the simplest tools in astrophysics. Magnetohydrodynamic models allowed scientists to treat charged particles and magnetic fields as a flowing, coupled medium, where density, velocity, pressure, and field geometry evolved together under conservation laws. By the late 20th century, increasingly complex computer simulations could include solar wind pressure, interstellar pressure, magnetic fields, neutral atoms, and the Sun's relative motion through nearby interstellar gas. These models were not childish guesses. They were serious attempts to translate physical law into a global shape. But they still depended on assumptions, because the region itself had never been sampled directly. Scientists had to estimate the density of the local interstellar medium from remote astronomical observations. They had to infer its magnetic field from indirect clues. They had to simplify the solar wind, even though the Sun changes with an approximately 11-year activity cycle, sending faster streams, slower streams, eruptions, pressure pulses, and magnetic disturbances outward over time. They had to decide whether to model the heliosphere as steady or time-dependent, smooth or irregular, symmetric or distorted. The earliest useful pictures often leaned toward simplicity, imagining the heliosphere as a roughly comet-like bubble moving through a surrounding medium, with a blunt forward region facing the incoming interstellar flow and a trailing structure downstream. Later models added more physics, but the basic expectation still remained. Voyager would move outward, meet the termination shock, cross the heliosheath, and eventually pass through the heliopause into interstellar space, in a way that, while scientifically rich, should still follow the broad script. This expectation gave the mission a quiet kind of suspense. The scientists knew they were waiting for signatures, not scenery. There would be no visible wall, no sudden dark curtain, no photograph of a glowing rim. The proof would come from instruments measuring charged particles, magnetic fields, plasma waves, and cosmic rays. A drop in low-energy particles from the Sun would mean the solar environment was weakening. A rise in galactic cosmic rays would suggest the spacecraft was leaving the shielded interior of the heliosphere. Changes in the magnetic field could mark the shift from solar magnetic influence to the larger magnetic architecture of the Milky Way. Plasma density, if measured directly or inferred through wave frequencies, could reveal whether the spacecraft was still surrounded by the rarefied solar wind environment or had entered the denser plasma just beyond the heliopause. In this way, the predicted edge of the solar system was less like a coastline seen from above and more like a diagnosis made from subtle changes in temperature, pulse, pressure, and breath. Before Voyager, it was also reasonable to believe that the heliosphere acted as a partial shield against galactic cosmic rays, those high-energy particles accelerated by violent processes throughout the galaxy, including supernova remnants and other astrophysical engines. These particles can penetrate deep into the solar system, but the magnetic turbulence and outward flow of the solar wind scatter and modulate them, so their intensity near Earth is not the same as it should be outside the heliosphere. If Voyager crossed the heliopause, cosmic ray intensity should rise, and by measuring that rise directly, scientists could learn how much protection the sun's bubble really provides. This mattered not only for abstract astrophysics, but for understanding the radiation environment of planets, spacecraft, astronauts, and perhaps even long-term changes in the near-Earth cosmic ray background as the sun moves through different galactic neighborhoods over thousands and millions of years. Still, for all its elegance, the pre-Voyager picture carried a hidden vulnerability. It made the edge of the solar system feel more orderly than nature had promised it would be. Plasma boundaries are not painted onto space. They are negotiated continuously by flows, waves, pressure pulses, magnetic tension, reconnection, turbulence, and time. The sun does not blow with perfectly steady breath. The interstellar medium is not a smooth, motionless sea. The magnetic field outside the heliosphere is not a rigid set of parallel lines drawn across the galaxy. Every variable in the model was alive in some way, and Voyager was about to enter the place where all those variables met. So before the first crossing, the expectation was clear enough to be tested. There should be a termination shock where the solar wind slows, a heliosheath where shocked solar plasma flows in a disturbed outer layer, and a heliopause where the solar system's plasma environment gives way to interstellar space. That was the map. That was the lantern. It was built from the best physics available, and it was not foolish. But as the spacecraft moved farther from the sun, carrying instruments older than many of the scientists who would later interpret their data, the universe began to answer in its own quieter language. The edge was real, but not simple. The layers existed, but they moved. The boundary could be crossed, but not always cleanly. The signs were there, but they did not line up exactly as expected. And the first great warning that the old map was incomplete would come at the termination shock, where the solar wind, after traveling billions of miles from the sun, finally began to slow under the pressure of the stars. The first clear warning that the old map was incomplete did not arrive as a dramatic picture, because there was nothing for Voyager to photograph, no shining rim around the solar system, no visible wall where sunlight ended, no border marked in the blackness like a line on a planetary chart. It arrived as a change in particles and fields, a quiet alteration in the invisible weather around a spacecraft already so far from the sun that Earth itself had become only a direction for a radio antenna to remember. For decades, scientists had expected the solar wind to meet resistance at a region called the termination shock, and the logic behind that expectation was strong. Near the Sun, the solar wind expands outward at hundreds of kilometers per second, moving faster than pressure waves can easily travel back through the plasma. So it behaves in a careful physical sense like a supersonic or supermagnetosonic flow. Not because it resembles wind in Earth's atmosphere, but because the charged particles and magnetic disturbances cannot communicate upstream quickly enough to smooth the coming collision with interstellar pressure. When a supersonic flow runs into an obstacle, a shock forms, and in the outer heliosphere, the obstacle is not a rock, a planet, or a wall, but the accumulated push of the local interstellar medium, a thin galactic presence made of particles, neutral atoms, magnetic fields, and pressure that becomes important only because the solar wind has weakened across billions of miles. The termination shock, then, was expected to be the place where the solar wind first lost its clean outward speed, where it slowed, compressed, heated, and entered the disturbed region later called the heliosheath. This was not supposed to be the final edge of the solar system, but it was the first great threshold, the moment when the Sun's plasma river began to feel the hand of the galaxy. Voyager 1 reached that threshold in December 2004 at about 94 astronomical units from the Sun, roughly 94 times the distance from Earth to the Sun, and immediately the result carried a quiet surprise because many estimates had placed the shock somewhat closer, often in a range that made 94 astronomical units feel like the outer edge of expectation rather than the comfortable center of it. One measurement alone would not have overturned the model, because the shock was never expected to be nailed into space with perfect rigidity. But even that first crossing made scientists listen more closely. The solar wind had traveled farther before slowing than some models had suggested, which meant the outward pressure of the Sun, the inward pressure of the interstellar medium, the magnetic structure of the heliosphere, or some combination of all three, had not been captured with enough precision. Then came something even more important than distance. The boundary did not behave like a fixed surface. Voyager's instruments saw conditions changing in ways that suggested the termination shock could move, breathe, and shift under the pressure of solar activity, and this made deep physical sense once the data were placed inside the long rhythm of the Sun. The Sun does not blow a perfectly steady wind. It rotates, erupts, changes its magnetic polarity, and moves through an approximately 11-year activity cycle, sending streams and pressure pulses outward like slow messages through the heliosphere. A strong solar outburst near the Sun does not reach the termination shock immediately. It must travel across tens of astronomical units, carrying enhanced pressure through interplanetary space, and when such a pulse finally arrives at the outer boundary, it can push the shock farther outward, just as a stronger breath can briefly inflate a membrane. When the pressure weakens, the shock can retreat inward again. In that sense, the termination shock is less like a landmark and more like a living contour in a plasma ocean. A surface defined by balance, and balances change when the forces on either side change. Voyager 1 did not find a simple mathematical shell sitting calmly in the dark. It found evidence of a boundary whose position was negotiated continuously by the Sun's changing wind and the surrounding galactic medium. This was the first slow fracture in the old confidence. But the second came from Voyager 2, which crossed the termination shock on August 30th, 2007, at about 84 astronomical units, almost 10 astronomical units closer to the Sun than Voyager 1's crossing. 10 astronomical units is not a small difference. It is roughly the scale of Saturn's distance from the Sun, a span so large that a spacecraft moving at tens of thousands of miles per hour still needs years to cover it. If the termination shock had been a smooth, spherical shell, equally distant in all directions and stable over time, the two spacecraft should have crossed it at more similar distances. Instead, Voyager 2 found the shock much closer, and the difference forced scientists to separate two possibilities that were probably both involved. The heliosphere might be asymmetric in shape, and the shock might also be moving with time. The two Voyagers were not following the same road. Voyager 1 was climbing northward out of the planetary plane on one trajectory, while Voyager 2 was moving southward along another. So they sampled different regions of the Sun's outer bubble, almost like two needles passing through different sides of a vast, flexible skin. Their crossings happened in different years, under different solar wind conditions, and through different heliospheric geometry. So the contrast between 94 astronomical units and 84 astronomical units did not mean a single simple thing. It meant the boundary was not the tidy, static object that a beginner's diagram might imply. The old model of a roughly symmetrical bubble could still provide a useful first approximation, but Voyager had begun to reveal the higher-order structure hidden beneath that approximation. Time dependence, latitudinal differences, magnetic pressure, solar cycle forcing, and the effect of the Sun moving through the local interstellar medium. In fluid and plasma physics, this is the difference between a drawing and a system. A drawing can show a clean arc labeled termination shock. A system must account for conservation of mass, momentum, energy, magnetic flux, particle populations, neutral atom interactions, and the fact that the solar wind itself is not uniform at all latitudes or at all times. The Voyagers had entered the regime where simple pressure balance had to give way to magneto-hydrodynamic modeling, with moving boundaries, anisotropic flows, and imperfectly known external conditions. That transition from elegant prediction to complicated reality is one of the deepest reasons the Voyager data mattered. It did not show that the earlier scientists were foolish. It showed that their models had been doing what models always do before direct measurement arrives, preserving the essential physics while hiding the messy richness that only the universe can provide. At the termination shock, the solar wind was expected to slow and heat. But even that process was not as simple as a textbook shock in ordinary gas. In a neutral gas, particles collide directly and redistribute energy through ordinary collisions. In the outer heliosphere, the plasma is so thin that direct particle collisions are rare. So the shock is largely collisionless, mediated by electromagnetic fields, waves, and collective behavior. This means particles can be reflected, scattered, and accelerated by magnetic irregularities, producing populations of energetic particles that carry information about the shock's structure. Voyager's instruments were not merely timing a crossing. They were sampling a plasma laboratory larger than the inner solar system, where the rules of collisionless shocks, cosmic ray modulation, and magnetic turbulence could be observed in a natural environment no experiment on Earth could reproduce. The shock also marked a change in the emotional scale of the mission. Until then, even in the deep outer solar system, Voyager was still moving through a realm where the solar wind streamed outward with a kind of youthful clarity. Beyond the termination shock, the spacecraft entered the heliosheath, where that wind was older, slower, hotter, and more disturbed, as though the sun's breath had reached the outskirts of its own strength and begun to fold back into turbulence. This shift mattered because it told scientists that the heliosphere was not simply a protective bubble with a clean surface, but a layered structure with an inner supersonic wind, a shock transition, a thick outer sheath, and then a final boundary still farther away. The shock was the first door, not the last one. Yet because that first door appeared in different places, at different distances, and under changing conditions, it warned that every later boundary might also be more subtle than expected. If the termination shock could move, the heliopause might move. If the shock was asymmetric, the heliosphere might be shaped by forces more complex than a smooth interstellar headwind. If particle behavior near the shock differed from expectation, then the heliosheath might contain hidden transport pathways, magnetic structures, and energetic populations not yet included in the simplest models. In the darkness beyond the planets, Voyager was teaching scientists a careful lesson without ever speaking in words. The edge of the solar system is not a place, where one influence simply stops and another begins, but a region where motion, pressure, magnetism, and time negotiate every boundary. And as Voyager moved beyond the termination shock into the heliosheath, the suspense deepened, because the next region was supposed to be only a disturbed outer layer of solar plasma, a transitional zone before the true interstellar medium. Instead, it would begin to show hints that particles from the galaxy were already finding their way in. Solar particles were already leaking away, and the clean separation between inside and outside was beginning to dissolve long before the final crossing. After Voyager crossed the termination shock, it did not enter interstellar space immediately. And this is one of the most important details in the entire story, because the edge of the solar system is not a single border, but a layered environment. And beyond the shock, there waited a vast, unsettled region called the heliosheath, a name that sounds almost soft, like a covering or a veil, though physically it describes one of the most complicated plasma landscapes ever measured directly by a human-made spacecraft. In the older models, the heliosheath had a fairly clear role. It was supposed to be the outer cushion of the heliosphere, the region where the solar wind, having slowed at the termination shock, continued moving outward and sideways in a hotter, denser, more turbulent form until it finally met the heliopause. That picture was not wrong in the broadest sense, but it was too clean, too geometrical, too much like a carefully shaded diagram in which one layer leads naturally to the next. Voyager found something closer to a disturbed sea. The solar wind beyond the termination shock was no longer the fast, organized river it had been inside the inner heliosphere. It had become slower, warmer, compressed, and magnetically restless, carrying the memory of the sun while already feeling the pressure of the galaxy ahead. In a simple fluid, one might imagine a stream slowing at a shock and then flowing smoothly around an obstacle. But the heliosheath is not a simple fluid. It is plasma, and plasma carries magnetic fields within it, responds collectively to electric and magnetic forces, supports waves that have no exact counterpart in ordinary air or water, and contains multiple particle populations that do not all share the same temperature, speed, or origin. The solar wind ions, pickup ions, anomalous cosmic rays, galactic cosmic rays, electrons, neutral atoms, and magnetic irregularities all coexist there in a strange conversation of pressure and motion. A pickup ion, for example, begins as a neutral atom from interstellar space drifting into the heliosphere. After sunlight or charge exchange strips or changes its electron state, it becomes ionized and is picked up by the solar wind's magnetic field, suddenly forced to join the outward flow. These particles can carry a large share of the pressure in the outer heliosphere, and because they behave differently from ordinary solar wind particles, they complicate the energy balance that a simple model might otherwise handle too easily. Before Voyager, many scientists expected the termination shock to be an efficient place for accelerating anomalous cosmic rays, those energetic particles thought to arise from interstellar neutral atoms that had been ionized and energized inside the heliosphere. But Voyager did not find the simple acceleration peak exactly where some models had expected it. That alone suggested that acceleration might be spread across broader regions, shaped by turbulence, magnetic geometry, or processes not fully captured in the earlier calculations. So as Voyager moved through the heliosheath, it was not merely crossing an empty waiting room before interstellar space. It was moving through a laboratory of collisionless plasma physics, where shock acceleration, particle diffusion, magnetic turbulence, and large-scale pressure balance were all operating at once across distances larger than the planetary system itself. The thickness of this region also mattered. Voyager 1 crossed the termination shock near 94 astronomical units, and later reached the heliopause near 121 astronomical units, implying that, along its path, the heliosheath extended for roughly a few dozen astronomical units. Voyager 2 crossed the termination shock closer in, near 84 astronomical units, and reached the heliopause near 119 astronomical units, giving a different thickness along a different route. These numbers are not just milestones, they are measurements of shape. They tell us that the outer heliosphere is not a perfect shell, and that the heliosheath changes depending on direction, solar cycle timing, and the larger pressure environment outside the sun's bubble. Inside this region, Voyager saw evidence that the flow was not simply rushing outward at a steady pace. In some interpretations, especially from Voyager 1's energetic particle and magnetic field data, the plasma near the outer heliosheath appeared to enter a kind of stagnation region where outward flow slowed dramatically and the magnetic field became stronger, as though the solar material had reached a place where it could no longer easily advance. This idea has to be handled carefully, because Voyager 1's plasma instrument was no longer returning direct solar wind plasma measurements by then, so scientists had to infer some conditions indirectly from particles, fields, and other instruments. Voyager 2, with its working plasma instrument, later provided a clearer comparison from another direction. But even with those limitations, the pattern was unmistakable in a broader sense. The heliosheath was not behaving like a simple conveyor belt carrying shocked solar wind cleanly to the heliopause. It had internal structure. It had regions where particles changed gradually, regions where intensities rose and fell, and regions where the magnetic and particle signatures seemed to anticipate the boundary before the boundary was officially crossed. This is where the story begins to feel almost eerie, because the spacecraft started detecting signs of the galaxy before it had fully left the Sun's domain. Galactic cosmic rays, high-energy particles from outside the heliosphere, became more intense as Voyager moved deeper into the heliosheath. That was expected in a general sense, because the Sun's shielding weakens outward, but the details were more subtle. The increase did not simply wait until the heliopause, like a curtain rising all at once. It began in stages, shaped by magnetic access, turbulence, and the changing ability of charged particles to diffuse through the outer heliosphere. At the same time, lower energy particles associated with the Sun began to decline in ways that suggested the heliosheath was connected to interstellar space more intricately than older boundary pictures had implied. Charged particles do not travel through this region like dust moving in straight lines. They spiral around magnetic field lines, scatter off irregularities, drift through gradients, and respond to structures that can open or restrict pathways. This means the heliosheath is partly a filter, partly a reservoir, and partly a gate, controlling how particles from the galaxy enter the heliosphere and how particles from the Sun escape outward. Its behavior determines how effectively the heliosphere shields the inner solar system from cosmic radiation, and that makes it more than a distant curiosity. The quiet plasma beyond Neptune is connected, through physics, to the radiation environment experienced by planets, spacecraft, and any future astronauts traveling far from Earth. In the older view, the heliosphere shielded the solar system in a broadly understandable way, with the heliosheath as one layer of modulation. But Voyager showed that the shielding is not a smooth wall. It is a dynamic magnetic environment with structure, variation, and directional dependence. The heliosheath also had to be understood through geometry. The Sun is moving through the local interstellar medium, and this motion means the heliosphere is shaped by a kind of galactic headwind, though the reality is more complex than a boat moving through water, because magnetic fields, neutral atoms, and plasma pressures all take part. In early images and simulations, it was tempting to picture a compressed nose and a long trailing tail. But the exact shape depended on quantities that were not well known before Voyager: the strength and direction of the interstellar magnetic field, the density of neutral hydrogen nearby, the speed and pressure of the solar wind at different solar latitudes, and the way charge exchange transfers energy between neutral atoms and ions. Charge exchange is especially important because neutral atoms can cross magnetic boundaries more freely than charged particles. When they exchange electrons with ions, they can create new energetic neutral atoms and alter the distribution of momentum and energy in the heliosheath. Later missions, such as IBEX, would map energetic neutral atoms remotely and reveal global features of the heliosphere that Voyager could only sample along narrow paths. But Voyager provided the in-place truth, the direct measurements, the feeling of the plasma under the fingertips of instruments. And because Voyager sampled only 2 trajectories, the heliosheath remains partly known and partly unknown, like a vast coastline explored by 2 tiny boats sailing through different fog banks. That limitation is not a weakness of the mission. It is part of the intellectual honesty of the science. From 2 paths, scientists can confirm that the region exists, that it is thick, disturbed, asymmetric, and filled with unexpected particle behavior. But they cannot fully map every latitude, longitude, and time variation. Models must still evolve, and every model has to respect the fact that the Sun itself changes. A solar maximum can send stronger disturbances outward, and years later, those disturbances can reach the heliosheath, reshape local conditions, alter particle intensities, and push on boundaries that had seemed stable. The delay between an event near the Sun and its effect near the heliopause gives the entire outer heliosphere a slow memory. It remembers storms that happened years earlier. It carries old pressure pulses outward like messages written in plasma. In this sense, the heliosheath is not only a place, but a record, a deep archive of solar activity stretched across billions of miles. For a viewer on Earth, where the Sun rises each day with familiar brightness, it is almost impossible to feel how far this influence extends. But Voyager turned that abstraction into measurement. The Sun's breath, weakened and disturbed, still fills the heliosheath. Yet every mile outward makes the galaxy more present. This is why the region is so powerful as a scientific idea. It is not inside in the simple way Earth is inside. It is not outside in the interstellar way. It is the in-between. And nature often hides its most interesting physics in in-between places. Shorelines, atmospheres, magnetopauses, shocks, transition layers, and boundaries where one regime gives way to another without surrendering cleanly. By the time Voyager moved through the heliosheath, the old model had not been destroyed, but it had been humbled. The broad architecture was there: termination shock, heliosheath, heliopause. But the texture was richer than expected. The region was thicker in some directions, more dynamic over time, more entangled with cosmic rays, more influenced by pickup ions and magnetic turbulence, and less obedient to the simple image of solar plasma flowing steadily toward a final wall. And then, as Voyager 1 moved closer to the outermost part of this disturbed sea, something even stranger began to appear. A region where particles seemed to find a highway along magnetic field lines, where solar particles could stream outward and galactic particles could slip inward, as if the boundary ahead was not closed at all, but quietly opening pathways between the Sun's fading breath and the dark, charged ocean of interstellar space. As Voyager 1 moved through the outer heliosheath, scientists were watching for a clean sign that the spacecraft had reached the heliopause. But what arrived first was not the final border, not the simple crossing that many diagrams had quietly prepared everyone to expect, and not the neat sequence of solar particles fading away while galactic particles rose in one decisive motion. Instead, the spacecraft entered a region so unexpected that researchers gave it an almost mythic name: the magnetic highway. The phrase sounds poetic, but it came from a real physical puzzle, one written in charged particles and magnetic fields rather than in light. In ordinary human imagination, a boundary separates two places by blocking motion, like a wall between rooms or a shoreline between land and sea. But in plasma physics, boundaries can be porous, threaded, folded, and connected by magnetic geometry. And charged particles do not simply drift across them the way dust might float through air. A proton or electron moving through space feels the Lorentz force, curving around magnetic field lines, spiraling in tight or broad helices depending on its energy, charge, and the strength of the field. And because of that motion, magnetic fields become more than invisible decoration. They become roads, fences, channels, and sometimes open doors. In the heliosheath, Voyager 1 began to see something that suggested the outer boundary of the Sun's bubble was not sealed. Low-energy particles associated with the heliosphere began dropping sharply, while higher-energy galactic cosmic rays from outside began rising, not in the final, fully confirmed way that would come later at the heliopause, but in a strange intermediate pattern that seemed to say the spacecraft was still inside the Sun's outer environment and yet already connected to the galaxy beyond. This was the haunting part. Voyager had not yet crossed into interstellar space by the later interpretation, but particles were behaving as if some of them had found a way through. The best way to picture this is not as a door opening in a wall, but as magnetic field lines creating pathways along which charged particles could stream. If solar particles could escape outward more easily, and galactic cosmic rays could enter inward more easily, then the boundary region was not merely a passive shell, it was an active magnetic structure where access depended on field topology. In plasma physics, topology matters because magnetic field lines can guide motion over enormous distances. And when regions of different magnetic influence press together, the structure can become complicated by draping, turbulence, reconnection-like behavior, and local alignments that allow particles to move in ways a global model might smooth over. The magnetic highway did not mean Voyager found a literal road. It meant Voyager found a region where particle transport suddenly became more organized along magnetic pathways, where the usual filtering behavior of the heliosheath changed, and where the difference between inside and outside became less like a border and more like an exchange. This is why the discovery was so powerful for heliophysics. Before direct measurement, models could represent the heliopause as a mathematically useful surface, the place where solar wind pressure yielded to interstellar pressure. But magnetic connectivity is not always captured by a simple surface. A boundary can have local structure. It can have regions where field lines are stretched, compressed, layered, or aligned in ways that create preferred directions for particle motion. It can allow some particle energies through more easily than others. It can look sharp in one measurement and gradual in another, depending on whether the instrument is measuring plasma density, energetic particles, magnetic direction, or wave activity. Voyager 1's data forced scientists to hold several facts together at once, and the tension between those facts created the suspense that lasted for months. The spacecraft saw a major decrease in particles thought to originate inside the heliosphere. It saw a rise in galactic cosmic rays, which should become more abundant outside the Sun's protective bubble. Yet the magnetic field direction did not rotate dramatically, as many scientists had expected it might when crossing from a solar-dominated magnetic environment into the local interstellar magnetic field. That lack of a clean magnetic rotation made the interpretation difficult. Some researchers thought Voyager might have crossed the heliopause already. Others argued it had entered a new outer layer, a previously unknown transition zone, still connected to the Sun, but increasingly open to interstellar particles. The magnetic highway became the name for that strange interval where the particle evidence seemed to lean toward escape and entry, while the magnetic evidence did not yet give the expected final signal. This is the kind of moment that makes space science feel both rigorous and deeply alive. The instruments were returning numbers, not metaphors, yet the numbers refused to arrange themselves into the old story. The universe was not contradicting physics. It was revealing which parts of the physics had been oversimplified. In charged particle transport, intensity changes depend not only on location, but also on diffusion coefficients, scattering conditions, magnetic turbulence, pitch angle distributions, particle energy, and the geometry of the field lines available to guide motion. A galactic cosmic ray does not simply decide whether it is inside or outside. It moves through a magnetic landscape, sometimes scattered, sometimes mirrored, sometimes guided inward along a path that becomes temporarily favorable. Likewise, lower energy heliospheric particles can leak outward if the field structure allows them to escape. When Voyager 1 entered the magnetic highway region in 2012, it was sampling this hidden architecture directly, and the data suggested that the outer heliosphere contained channels of communication between the solar domain and interstellar space. One of the deeper lessons here is that the heliosphere is not only shaped by pressure, but also by information carried through fields. Pressure balance can tell us where a boundary might form, but magnetic connectivity can determine how particles actually move through and around that boundary. In magnetohydrodynamics, the magnetic field is frozen into the plasma only under ideal conditions. But real space plasmas contain turbulence, kinetic effects, and non-ideal processes that can loosen that simple picture. The global heliosphere may be modeled as a bubble, but local regions near the heliopause can develop layered magnetic sectors, compressed fields, and particle escape routes that behave nothing like the smooth surfaces drawn in introductory diagrams. The magnetic highway therefore marked a shift from thinking of the edge as a location to thinking of it as a process, a boundary system with internal states. It also reminded scientists that Voyager was only one moving point, one thin line through a vast three-dimensional structure. If the spacecraft crossed a region of unusual magnetic connection, that did not necessarily mean the entire heliopause looked the same everywhere. Voyager 2, following a different path years later, would give another comparison, but even two spacecraft cannot map the whole sky. The magnetic highway may have been a local feature near Voyager 1's trajectory, or part of a broader outer heliosheath structure, or a manifestation of how the Sun's magnetic field was interacting with the local interstellar field at that particular time in the solar cycle. Each possibility carries different implications, and the honest scientific answer is not to force certainty where the data do not fully allow it, but to see the feature as a clue to a more intricate boundary than the old models had assumed. What made the discovery even more compelling was its timing. It appeared just before Voyager 1's later, widely accepted heliopause crossing in August 2012, when heliospheric particles dropped to very low levels and galactic cosmic rays rose to a new, sustained intensity. The magnetic highway was like the dimly lit corridor before the final door, a region where the galaxy's presence was already entering the measurements before the spacecraft fully stepped outside the Sun's plasma bubble. For a viewer, this may sound subtle, but for scientists, it was profound. It meant that the edge of the solar system could not be defined by one instrument alone. Energetic particles told part of the story. Magnetic fields told another. Plasma waves would later tell a crucial third story by revealing electron density outside the heliopause. Only by combining all of them could the boundary be understood. That is how advanced space physics often works. Not through one dramatic answer, but through converging signatures, each imperfect alone, each powerful in combination. The magnetic highway sat exactly in that difficult, beautiful space between certainty and discovery. It did not erase the idea of the heliopause. It prepared scientists to see the heliopause as more complex than a simple final skin. It showed that before the sun's bubble ended, it frayed. It opened channels. It allowed exchange. It behaved like a living plasma boundary under stress from both the solar wind behind it and the interstellar medium ahead. And in the silence of that region, far beyond the planets, Voyager 1 became less like a spacecraft crossing a line and more like a small needle passing through the fabric of a cosmic membrane, feeling where the threads tightened, where they loosened, and where they quietly connected two different realms. This is why the magnetic highway belongs at the center of the Voyager story. It was not the final answer, but it was the warning that the final answer would not be simple. The old expectation had been that the spacecraft would move from solar space to interstellar space through a boundary that announced itself cleanly. Instead, Voyager found an approach zone where the particles began changing before the magnetic field gave the expected permission, where the galaxy seemed to whisper through the sun's outer shell, and where the language of the data became subtle enough that scientists had to slow down and rethink what crossing a boundary truly means. And then, after that strange corridor of magnetic access, after solar particles had begun vanishing and galactic cosmic rays had grown stronger, Voyager 1 reached the moment that would become one of the most important in the history of space exploration: the crossing of the heliopause itself, the place where humanity's first messenger finally stepped beyond the protective breath of the sun and entered the measured plasma of interstellar space. The moment Voyager 1 crossed the heliopause did not look like a crossing at all. At least, not in the way the human mind wants a boundary to look. Because there was no flash, no surface, no visible gate opening at the edge of the sun's domain. Only a small spacecraft moving through darkness while its instruments watched the invisible populations around it change with a suddenness that felt almost like a withheld answer finally being spoken. For years, scientists had been waiting for this moment, not because they expected spectacle, but because the heliopause was the boundary that would test the whole architecture of heliospheric science. The termination shock had already shown where the solar wind slowed. The heliosheath had revealed that the outer solar wind was disturbed, thick, turbulent, and more porous than expected. The magnetic highway had suggested that particles could find pathways across the outer boundary before the final transition. But the heliopause itself was different. This was supposed to be the place where the solar wind, in the deepest physical sense, stopped being the dominant plasma environment, where the outward flow from the sun yielded to the local interstellar medium, and where a human-made object would, for the first time, measure space no longer controlled primarily by our star. On August 25, 2012, Voyager 1 reached that threshold at roughly 121 astronomical units from the Sun, more than 11 billion miles from home. And the first evidence came through particles. Low-energy charged particles associated with the heliosphere dropped dramatically, as though the reservoir of solar material around the spacecraft had been drained away. At nearly the same time, galactic cosmic rays, those high-energy particles arriving from beyond the Sun's protective bubble, rose to a stronger and more stable level. This was exactly the kind of signature scientists had expected from a heliopause crossing, because inside the heliosphere, the solar wind and its magnetic turbulence scatter and reduce some of the incoming galactic cosmic rays, while outside the heliopause, those cosmic rays should appear with less modulation from the Sun. If the story had ended there, the announcement might have been immediate and clean. Voyager had left the heliosphere. But the universe rarely hands over its deepest answers without asking for patience. And one measurement did not fit the script. The magnetic field did not rotate in the dramatic way many models had suggested it might. Before the crossing, Voyager 1 measured a magnetic field shaped by the outer heliosphere. After the crossing, the direction remained surprisingly similar. This was not a small detail, because magnetic field direction had been considered one of the possible markers of the transition from the Sun's magnetic environment to the galactic magnetic field outside. In a simplified picture, the solar magnetic field, carried outward by the solar wind and wound into a spiral by the rotation of the Sun, should differ from the local interstellar magnetic field, which belongs to the larger structure of the Milky Way's neighborhood. Crossing the heliopause might therefore have been expected to produce a noticeable change in direction. Instead, Voyager found a boundary where the particles changed sharply, but the field direction remained nearly aligned. For months, this created a scientific hesitation, a kind of disciplined uncertainty that is easy to misunderstand from the outside, but is one of the most honest parts of real discovery. Some researchers argued that the disappearance of solar particles and the increase of cosmic rays were strong evidence that Voyager 1 had crossed the heliopause. Others suggested it might still be inside an unknown outer layer of the heliosphere, perhaps a region where particles had escaped but magnetic connection to the Sun remained. The spacecraft had entered a place that behaved like interstellar space by particle evidence, yet did not offer the magnetic rotation that many had imagined as the final signature. The debate was not confusion in the weak sense. It was science doing what it must do when nature gives overlapping clues instead of a single clean label. A boundary in plasma physics is not defined by one number alone. It has particle populations, magnetic geometry, density structure, wave behavior, and time-dependent motion. And each instrument sees only one face of a larger truth. What finally strengthened the conclusion was not a photograph, not a direct plasma reading from Voyager 1's plasma instrument, which was no longer functioning, but something subtler and almost more beautiful: plasma waves. In 2013, Voyager 1's plasma wave instrument detected oscillations in the surrounding plasma, likely excited by disturbances that had traveled outward from the Sun and reached the interstellar medium beyond the heliopause. The frequency of those oscillations allowed scientists to infer the electron density of the plasma around the spacecraft. Because in plasma physics, the natural oscillation frequency depends on how many free electrons are present. The inferred density was much higher than expected inside the heliosheath and consistent with the local interstellar medium just beyond the heliopause. This was the missing piece. Voyager 1 had not merely seen particles change, it was now surrounded by plasma with the density of interstellar space. The crossing was confirmed not by a single dramatic event, but by convergence. Heliospheric particles nearly vanished, galactic cosmic rays increased, and the plasma environment became denser in the way interstellar plasma should. The magnetic field mystery did not disappear, but it changed meaning. Rather than proving Voyager had not crossed, the lack of strong rotation suggested that the local interstellar magnetic field near Voyager 1's path was draped around the heliopause in a direction roughly similar to the field just inside the boundary, or that the boundary geometry and magnetic interaction were more subtle than global models had assumed. Magnetic draping is a natural possibility when a magnetized flow encounters an obstacle. Field lines can bend and wrap around the surface of the heliosphere, creating local alignments that make the transition look less abrupt in direction than expected. This does not make the heliopause unreal. It makes it more physical, more textured, less like a drawn line, and more like a membrane shaped by pressure, motion, and field tension. Then, 6 years later, Voyager 2 brought another essential piece of the story. On November 5, 2018, it crossed the heliopause at about 119 astronomical units from the Sun, traveling through a different region of the heliosphere and carrying a working plasma instrument that Voyager 1 no longer had. This made Voyager 2's crossing especially valuable because it could measure changes in the plasma directly. It observed a clear transition from the hotter, more tenuous heliosheath plasma into the colder, denser local interstellar plasma, while also detecting the expected drop in heliospheric particles and rise in galactic cosmic rays. The second crossing showed that Voyager 1's experience was not an isolated illusion, but it also showed that the boundary was not identical in every direction. Voyager 2 saw its own version of the heliopause, with its own particle behavior, plasma changes, and magnetic field details, reminding scientists that two spacecraft separated by direction and time were sampling different parts of a global, shifting structure. This matters deeply because the heliopause is often described as the edge of the solar system, but it is more accurate to call it the edge of the Sun's plasma bubble, not the edge of the Sun's gravity, and not the final boundary of every object bound to the Sun. The Oort cloud, if its vast predicted population of icy bodies is described correctly by current models, lies much farther out, and Voyager will take centuries just to approach its inner regions. So when we say Voyager entered interstellar space, we mean it entered the space between stars in the plasma sense, beyond the heliosphere, beyond the region dominated by the solar wind, inside the local interstellar medium. That distinction is not a correction meant to reduce the achievement, it makes the achievement sharper. Voyager did not leave the Sun's gravitational story, but it left the Sun's wind. It crossed from a medium made primarily by our star into a medium shaped by the galaxy around it. The heliopause crossing therefore changed the scale of human measurement. Before Voyager, interstellar space near the Sun was known through remote observation, absorption lines in starlight, theoretical modeling, and indirect inference. After Voyager, it became a place with in situ data, a real environment touched by instruments built on Earth. Its plasma density, magnetic field, cosmic ray intensity, and wave behavior were no longer only distant estimates. They were numbers returned from beyond the solar wind. Yet even in that triumph, the data refused to become simple. The heliopause was not a perfectly stable shell. Solar activity can send pressure waves outward, and when those disturbances reach the boundary, they may push, ripple, or shake it. Voyager's later detections of plasma oscillations beyond the heliopause suggested that the Sun can still disturb the interstellar medium even after its wind no longer flows freely there. In this way, the heliopause is not the place where the Sun becomes irrelevant. It is the place where the Sun changes the way it speaks. Inside, it speaks as wind. Outside, it may speak as waves, pressure disturbances, and delayed echoes moving through a denser galactic plasma. The crossing also reshaped the emotional meaning of Voyager itself. A spacecraft built for flybys of giant planets had become the first probe to pass through the boundary of the heliosphere. Its instruments, aging and power-starved, had done something no telescope could do from Earth. They had placed a measuring point in the dark borderland between stellar influence and galactic medium. The answer it brought back was precise, but also humbling. The edge of the Sun's bubble exists, but it is not a clean wall. It can be recognized by a collapse of solar particles, an increase in cosmic rays, a denser plasma environment, and a subtle magnetic field that may not obey the simplest expectation. It is a boundary of influence, not of ownership, a transition in plasma regime, not a mystical end of the solar system. And as Voyager 1 and Voyager 2 moved beyond it, they revealed that outside the heliopause, the galaxy is not empty, but waiting, filled with thin plasma, weak magnetic fields, high-energy particles, and waves faint enough to seem almost silent, yet strong enough to rewrite the way we understand our cosmic neighborhood. The most important part is this: Voyager did not merely cross a border. It taught us how difficult it is to define one. The Sun fades by layers. The galaxy arrives by degrees. And between them lies the heliopause, a moving, magnetized shore where the last breath of our star meets the quiet pressure of interstellar space, and where humanity first learned that leaving the solar system is not a single step into darkness, but a slow passage through invisible physics. When Voyager crossed beyond the heliopause, one of the clearest changes it measured was not a wall, not a surface, and not a sudden arrival into emptiness, but a change in radiation, a rise in the invisible rain of galactic cosmic rays that had been pressing against the Sun's outer bubble all along. To understand why this mattered so much, we have to slow down and look carefully at what cosmic rays really are, because the name can be misleading. They are not rays in the way sunlight is made of electromagnetic radiation, and they are not gentle beams shining through space. Most galactic cosmic rays are high-energy charged particles, especially protons, with smaller fractions of helium nuclei, heavier atomic nuclei, and electrons, traveling at speeds close to the speed of light after being accelerated by some of the most powerful engines in the galaxy. Many are thought to gain their energy in shock waves associated with supernova remnants, where an exploding star leaves behind expanding magnetic turbulence that can scatter particles again and again, pushing them to higher and higher energies through a process known as diffusive shock acceleration. Other sources may contribute as well, including pulsar wind nebulae, stellar explosions, and broader galactic environments where magnetic fields and plasma flows exchange energy across enormous scales. But the essential truth is this: cosmic rays are messengers from violent astrophysical processes far outside the comfortable planetary system we know. They cross interstellar space not in straight, easy lines, but by spiraling around magnetic field lines, scattering through turbulence, drifting through gradients and slowly losing the memory of exactly where they came from. By the time they reach the neighborhood of the sun, they are less like arrows pointing back to a single source and more like rain shaped by the weather of the entire galaxy. Before Voyager, scientists already knew that cosmic rays reached Earth because they had been detected in the atmosphere and by instruments in space for decades, and their effects are woven quietly into science itself. When cosmic rays strike atoms in Earth's upper atmosphere, they create cascades of secondary particles, producing isotopes such as carbon-14 and beryllium-10 that become useful records of radiation history, solar activity, and atmospheric chemistry. They matter for aviation, for spacecraft electronics, for astronauts, for planetary atmospheres, and for the long-term radiation conditions of worlds with and without magnetic fields. But near Earth, cosmic rays do not arrive in their untouched interstellar form because Earth sits deep inside the heliosphere, inside the magnetic breath of the sun. The solar wind, carrying the sun's magnetic field outward, does not block every cosmic ray, especially not the most energetic ones, but it modulates them. It scatters them, slows their entry, redirects their paths, and changes their intensity depending on solar activity. This is why cosmic ray levels near Earth tend to vary with the solar cycle. During periods of stronger solar activity, the heliosphere becomes more disturbed and magnetically turbulent, making it harder for many lower-energy galactic cosmic rays to penetrate inward. During quieter solar periods, more of them can reach the inner solar system. This modulation was known before Voyager reached the edge, but Voyager gave scientists something far more valuable: a direct comparison between cosmic ray intensity inside the heliosphere, through the heliosheath, and beyond the heliopause. That comparison turned the heliosphere from an abstract protective bubble into a measured shield. As Voyager 1 traveled outward through the heliosheath, galactic cosmic rays gradually increased, suggesting that the farther the spacecraft moved from the sun, the weaker the solar modulation became. This gradual rise already told a story. The heliosphere was not simply blocking cosmic rays at one final wall, but reducing their intensity across a broad, magnetically structured volume. The shield was not a solid dome. It was a vast region of moving plasma and turbulent fields, and its protection came from interaction, not from separation. Then, around the heliopause crossing in 2012, Voyager 1 measured a sharper change. Particles associated with the heliosphere dropped dramatically, while galactic cosmic rays rose to a higher, steadier level. Voyager 2 later saw its own version of this transition when it crossed the heliopause in 2018. Together, the two spacecraft confirmed that outside the heliosphere, the cosmic ray environment is stronger than the one measured inside the sun's bubble. This was one of the most important discoveries at the edge of the solar system, because it showed, in place and in real time, that the heliosphere acts as a filter between the planets and the galaxy. It does not make the inner solar system safe in an absolute sense, and it does not erase cosmic radiation, but it reduces and reshapes the flow of many charged particles before they reach the worlds orbiting the sun. In that sense, the sun protects not only by giving light, but also by creating a magnetic environment large enough to soften part of the galaxy's radiation weather. The physics of this shielding is subtle and beautiful. A charged particle entering the heliosphere encounters magnetic fields embedded in the outward flowing solar wind. Because the particle is charged, it curves around field lines rather than moving freely. And because the field is not smooth but turbulent, the particle can scatter, change direction, diffuse slowly inward, or be carried outward by the solar wind. The mathematical description involves transport equations, diffusion tensors, drift motions, adiabatic energy changes, and boundary conditions at the outer heliosphere, all of which attempt to describe how a population of particles moves through a magnetic plasma that is itself moving. In the simplest intuition, the heliosphere is like a wind blowing outward, against dust trying to fall inward. But that picture is too simple because cosmic rays are not dust, and the wind is not ordinary air. The real shield is electromagnetic, dynamic, and energy dependent. Very high energy cosmic rays can penetrate deeply with less resistance, while lower energy particles are more strongly modulated by solar magnetic activity. This is why Voyager's measurements were so valuable. They did not merely show that cosmic rays increased beyond the heliopause. They helped anchor the boundary conditions for models that try to explain how cosmic rays propagate through the entire heliosphere. The data also complicated the old picture, because cosmic ray access is not perfectly uniform. Charged particles respond to magnetic geometry, and if the local interstellar magnetic field drapes around the heliopause, if the heliosheath contains turbulent structures, if magnetic pathways open or close with solar conditions, then cosmic rays may enter more easily from some directions than others. Voyager's particle measurements suggested that the outer heliosphere is not a smooth, equal shield from every angle, but a structured magnetic environment where direction, energy, and time all matter. This connects back to the magnetic highway, because any region that allows particles to stream more freely along field lines can change the way cosmic rays leak inward and heliospheric particles escape outward. The shield is real, but it has texture. It has seams, currents, waves, gradients, and changing access routes. That is more interesting than a perfect wall, because a perfect wall would be easy to describe and almost lifeless in comparison. The heliosphere is closer to a living weather system, with the sun at its center and the galaxy pressing softly from outside. The discovery also carries a deeper implication for Earth, though we must be careful not to exaggerate it. Earth has its own magnetic field and atmosphere, which provide strong protection against charged particles, and life on the surface is shielded by layers of defense far closer than the heliopause. But the heliosphere is the outermost layer of that protection, the first broad filter that the galaxy encounters before its particles move inward toward the planets. If the sun travels through different regions of the interstellar medium over long time scales, and if the heliosphere changes size or shape as external pressure changes, then the level of cosmic ray modulation reaching the inner solar system could also change. Some researchers have explored whether variations in cosmic ray flux might influence atmospheric chemistry, cloud nucleation, climate-related processes, or biological mutation rates across geological time. But these links are complex and not settled in a simple one-cause way. What Voyager firmly established is the physical foundation. The heliosphere modulates cosmic rays, and outside the heliopause, the radiation environment is different. From there, careful science can investigate consequences without turning possibility into certainty. For future exploration, the finding is even more direct. Any spacecraft leaving the heliosphere, any probe designed for interstellar precursor missions, and certainly any imagined human journey beyond the Sun's protective bubble would face a radiation environment closer to what Voyager measured outside the heliopause. Electronics would need shielding and hardening. Instruments would need to account for background particle hits. Biological travelers, if they ever went so far, would require protection far beyond what a simple spacecraft hull could provide. Voyager did not solve interstellar travel, but it measured one of its unavoidable environments. It told us that interstellar space near the Sun is not empty darkness. It is crossed by energetic particles carrying the history of stellar death, galactic magnetic fields, and plasma shocks from distant places. And still, there is something strangely calming in that knowledge. The Sun is small compared with the Milky Way, and yet its wind carves out a domain large enough to soften the cosmic rain around us. Our planet rests deep inside that domain, beneath the heliosphere, beneath Earth's magnetosphere, beneath the atmosphere, beneath layers of protection we rarely notice because they work silently. Voyager revealed that the edge of the solar system is not only a boundary of particles and fields, but a boundary of shelter. Inside it, the Sun's presence is still strong enough to reduce part of the galaxy's radiation. Outside it, the universe becomes more exposed, more direct, more ancient in the messages it sends. And as Voyager moved beyond that invisible shield, counting cosmic rays in the darkness, it showed us that our solar system is not merely a family of planets around a star, but a protected island of plasma drifting through a sea of high-energy messengers from the wider galaxy. The next question was even stranger. If cosmic rays proved the shield was real, then plasma waves would reveal what the space beyond that shield was made of, and Voyager would begin to hear, in the faintest possible way, the density and texture of interstellar space itself. After cosmic rays showed that the Sun's bubble was a real shield, Voyager revealed something quieter, stranger, and in some ways even more intimate. The space beyond the heliopause was not empty, and the proof came through waves so faint that they felt less like a signal and more like a whisper traveling through the dark. To say Voyager heard interstellar space is poetic, but it is also close to the truth if we understand the word carefully. Because the spacecraft was not recording sound in the way a microphone records air pressure on Earth. There is no ordinary air out there to carry human sound. No wind moving through leaves. No thunder rolling across a sky. No ocean surf breaking against a shore. What Voyager detected were plasma waves, oscillations in a thin gas of charged particles. And these waves allowed scientists to measure something profoundly important: the electron density of the local interstellar medium around the spacecraft. That detail may sound technical at first, almost too small to feel dramatic, but it became one of the strongest clues that Voyager 1 had truly crossed beyond the Sun's plasma bubble. The reason is elegant. A plasma is not just a gas. It is a gas in which some atoms have been separated into charged particles, with electrons moving freely enough that electric and magnetic forces shape the collective behavior of the medium. If you disturb a plasma, the electrons can slosh back and forth against the more massive ions, creating natural oscillations. The frequency of those oscillations depends on how many free electrons are present. More electrons mean a higher plasma frequency. Fewer electrons mean a lower one. In the simplest physical form, the plasma frequency scales with the square root of electron density. So by measuring the tone of the plasma's vibration, scientists can infer how many electrons are present in a cubic centimeter of space. It is almost like learning the depth of a hidden lake by listening to the way it rings. This mattered because Voyager 1's direct plasma instrument was no longer functioning by the time it reached the heliopause, so scientists could not simply read the local plasma density in the most straightforward way. They had to wait for the universe to provide a different kind of measurement. The plasma wave instrument, designed to detect electric field oscillations, became a kind of scientific ear, sensitive to the weak tremors of charged particles around the spacecraft. Then, after Voyager 1's particle instruments saw heliospheric particles vanish and galactic cosmic rays rise, the plasma wave data provided the deeper confirmation. The surrounding plasma was denser than the plasma expected inside the heliosheath, consistent with the local interstellar medium. This was not an emotional guess, it was a physical inference based on wave frequency. Inside the heliosphere, the solar wind plasma is extremely thin in the outer regions, spread thin by the enormous expansion of the sun's outflow. Outside the heliopause, the interstellar plasma is still extraordinarily rare by earthly standards, but compared with the outer heliosheath, it is denser. That difference is one of the fingerprints of crossing the boundary. When Voyager 1 detected plasma oscillations with frequencies indicating a higher electron density, the data helped resolve the debate created by the magnetic field mystery. The particles had already suggested the spacecraft was outside. The cosmic rays had already risen. The solar particles had nearly disappeared. But because the magnetic field direction did not rotate as dramatically as expected, scientists needed another signature, and the plasma waves gave it to them. The spacecraft was surrounded by the kind of plasma that belongs beyond the heliopause. In a way, the galaxy had answered through vibration. The waves themselves may have been triggered by disturbances from the sun, which is one of the most beautiful ironies in the Voyager story. Even after the spacecraft had crossed beyond the region where the solar wind dominates, solar activity could still send pressure pulses outward across the heliosphere, and when those pulses reached the heliopause, they could disturb the interstellar plasma beyond it. The result was a faint ringing in the local plasma, a tone Voyager could detect long after the original solar event had left the inner solar system behind. This means the sun did not stop speaking at the heliopause. It changed language. Inside the heliosphere, it spoke through wind, particles, and magnetic turbulence. Outside, it could still send echoes, shock-like disturbances, and wave energy into the nearby interstellar medium. Plasma waves therefore revealed two things at once: that Voyager was in denser interstellar plasma, and that the boundary between the Sun and the galaxy remained dynamically connected. The heliopause was not a sealed container. It was a surface of interaction, able to transmit disturbances from one side to the other. For viewers, this may be one of the most important ideas to hold gently in the mind. Interstellar space is not empty black silence. It is not dense, it is not warm in a human sense, and it would not feel like anything to the body. But it has structure. It has charged particles, neutral atoms, magnetic fields, pressure waves, turbulence, and density variations. A cubic centimeter may contain far less matter than any earthly vacuum we can easily imagine. Yet across billions of miles, that thinness becomes a medium. It can push back on the heliosphere. It can carry waves. It can guide cosmic rays. It can be measured. Voyager turned the phrase "space between stars" from an abstraction into a local environment with numbers. Scientists could estimate electron density not by looking through a telescope at distant starlight, but by using a spacecraft sitting inside the medium itself, quietly measuring how the plasma around it trembled. This is a different kind of knowledge from images of planets. A photograph gives shape and color. A plasma wave gives presence. It says, "There is something here, even when your eyes would see nothing." That is why the plasma wave detections are so central to the Voyager discovery. They transformed interstellar space from a philosophical emptiness into a measurable physical substance, thin beyond intuition, but real enough to ring. The data also opened a new way to think about the local interstellar medium. Its density was not perfectly uniform. Different oscillation events suggested variations over distance, meaning Voyager was not moving through a smooth, featureless gas, but through a medium with texture. Small changes in density may reflect turbulence, waves, remnants of larger interstellar structures, or variations shaped by the interaction between the heliosphere and the surrounding galactic environment. The local interstellar medium near the Sun is part of a larger region, sometimes described as the local interstellar cloud, a warm, partially ionized cloud through which the solar system is currently traveling. The heliosphere is shaped by this cloud's density, temperature, flow speed, and magnetic field, and Voyager's plasma wave measurements gave one of the first direct local tests of those properties just beyond the Sun's bubble. Still, the interpretation requires humility, because Voyager samples only one narrow path through a vast three-dimensional environment. A density measured along Voyager 1's trajectory is not automatically the density everywhere around the heliosphere. Voyager 2 provided another path, and together the two spacecraft improved the picture. But the galaxy around the Sun remains only partially mapped at this scale. That partial knowledge is not a failure. It is the honest condition of deep space exploration. Two tiny machines are tracing two thin lines through an invisible ocean. And from those lines, scientists infer the shape, pressure, and texture of a boundary larger than the planetary system. Plasma waves also deepen the meaning of the word edge. If the heliopause were a simple wall, one might imagine that outside it everything would become unrelated to the Sun. But the waves show that influence can cross a boundary even when plasma flow does not. The solar wind may not dominate beyond the heliopause, but solar disturbances can still shake the plasma just outside it. This is similar in spirit to waves traveling beyond a shoreline after a storm has struck the coast, though the physics is electromagnetic rather than oceanic. The boundary separates two regimes, but not two completely disconnected realities. This is why Voyager's discovery is more subtle than the phrase "left the solar system" often suggests. It entered interstellar plasma, yes, but it remained near a living boundary, close enough to hear the delayed echoes of the star that made it. There is something deeply quiet in that image. A spacecraft built by humans moving through darkness beyond the sun's wind, detecting the faint ringing of plasma disturbed by events that began near the star it left behind. The measurement is scientific, but the scale is almost meditative. A solar eruption may happen near the sun, pass the planets, travel for months or years through the outer heliosphere, reach the heliopause, disturb the interstellar medium, and finally cause electrons around Voyager to oscillate at a frequency that tells Earth how dense that darkness is. By the time the data returns home, carried by a radio signal weaker than a whisper, the original event has become part of a chain of cause and measurement stretching across billions of miles. This is how Voyager made the emptiness speak, not by hearing sound, but by detecting the natural music of charged matter. And once scientists knew that the plasma beyond the heliopause could ring, they also knew that interstellar space near the sun had weather of its own. A faint, slow, magnetized weather written in waves, density changes, and cosmic rays. The next discovery would make that weather feel even more alive, because the same waves that confirmed the density of interstellar plasma also showed that the sun could send disturbances beyond its own bubble, causing the edge of the solar system to tremble like a distant membrane in the dark. The deeper Voyager moved beyond the heliopause, the more the edge of the solar system stopped resembling an edge at all. Because a true edge, in the ordinary human imagination, is supposed to stay where it is, like the rim of a table, the shore on a map, or the final line of a country drawn in ink. But the boundary Voyager measured was not drawn in ink. It was written in plasma, pressure, magnetic fields, and time. The heliosphere is shaped by balance, and balance is never entirely still when the forces involved are alive. The sun does not release a perfectly steady wind. It breathes unevenly. It turns once every few weeks, changes its magnetic structure across an approximately 11-year solar cycle, sends fast streams from coronal holes, releases slower solar wind from other regions, erupts in coronal mass ejections, and launches pressure pulses that travel outward through the solar system like slow thunder rolling away from a storm. Near Earth, a strong solar event may disturb satellites, brighten auroras, or shake the magnetic environment around our planet within days. But in the outer heliosphere, the same event becomes something much more patient. It must cross the orbits of the giant planets, pass through the distant solar wind, move across tens of astronomical units, and only after months or years can it reach the termination shock, the heliosheath, or the heliopause. This means the outer edge of the solar system is not responding to the sun we see today, but to the sun as it was years earlier. It is a delayed memory of solar weather stretched across billions of miles. Voyager revealed that this memory is not abstract. It can physically move and disturb the boundary. When a stronger wave of solar wind pressure travels outward, it can push on the termination shock or the heliopause, temporarily changing their positions. When that pressure weakens, the boundary can relax inward again. The result is a kind of breathing, not biological breathing, of course, but a plasma breathing, an expansion and contraction governed by momentum, magnetic pressure, thermal pressure, and the surrounding interstellar medium. The image is gentle, but the physics is exact. A boundary defined by pressure balance will shift when the pressure changes. In the case of the heliopause, the outward influence comes from the solar wind and its magnetic field, while the inward resistance comes from the local interstellar medium, including its plasma, neutral atoms, cosmic rays, and magnetic field. Change either side, and the surface of balance moves. Voyager gave scientists the first direct reason to take that motion seriously. The termination shock had already shown signs of movement when Voyager encountered it at different distances and under changing conditions. But beyond the heliopause, the evidence became even more haunting, because Voyager 1 began detecting plasma oscillations in interstellar space that appeared to be linked to solar disturbances arriving long after they had left the inner solar system. These were sometimes described in public-facing language as tsunami waves, not because they were ocean waves, but because they were broad disturbances moving through plasma, compressing and rarefying the charged particles around the spacecraft. A solar eruption near the Sun can send a shock or pressure wave outward through the heliosphere. When that disturbance reaches the heliopause, it can strike the boundary like a soft hammer on a cosmic membrane, and part of the disturbance can be transmitted into the local interstellar plasma beyond. Voyager's plasma wave instrument could then detect the resulting oscillations, not as sound for human ears, but as electric field vibrations caused by electrons moving collectively through the thin interstellar medium. These waves were valuable because they allowed scientists to infer plasma density, but they were also valuable because they showed that the heliopause is dynamically connected to both sides of the boundary. The solar wind itself does not simply continue outward as the dominant flow after the heliopause, but solar disturbances can still make the nearby interstellar medium ring. That distinction is subtle and important. The Sun's wind is confined by the heliopause, yet the Sun's influence can still be transmitted as waves and shocks beyond it. In this way, the edge of the solar system behaves less like a sealed wall and more like a shoreline, where storms on one side can send vibrations into the water on the other. The old simplified picture had often treated the heliopause as a relatively stable surface, perhaps moving slowly with the solar cycle. But Voyager showed that shorter-term events also matter, because the outer heliosphere carries pressure structures outward over time. A coronal mass ejection or a merged interaction region can evolve as it travels, combining with other streams, steepening into shocks, weakening, broadening, and changing shape. So by the time it reaches the far outer heliosphere, it is not the same compact event that left the Sun. It has become a large-scale pressure front, a memory of several solar events braided together by distance. In plasma physics, this is expected in principle, but direct measurement gives the idea weight. It means that the boundary Voyager crossed is not merely shaped by average conditions, but also by the history of disturbances passing through it. The heliosphere, then, has weather, and like all weather, it has layers of time. There is the fast weather of solar eruptions near the Sun, the slower weather of pressure pulses crossing the outer solar system, the long weather of the 11-year solar cycle, and the very long weather of the Sun's motion through different parts of the local interstellar environment. Each scale can reshape the boundary in its own way. Over years, solar activity can make the heliosphere expand or contract. Over thousands of years, changes in the local interstellar medium may alter the external pressure around the Sun. Over millions of years, the solar system's galactic journey may carry it through regions with different density, ionization, and magnetic field strength, potentially changing the size of the heliosphere and the degree of cosmic ray shielding it provides. Voyager measured only a tiny portion of this grand system, But even that tiny portion was enough to show that the boundary is alive with motion. This breathing quality also complicates the meaning of crossing. If a spacecraft sits near the heliopause and the boundary moves across it, then the spacecraft could, in principle, experience changing conditions without traveling very far relative to the Sun. A boundary can pass over the spacecraft just as much as the spacecraft can pass through the boundary. This is not merely a philosophical detail. It affects how scientists interpret particle intensities, magnetic fields, and plasma signatures near the edge. A sudden rise or fall in certain particles might reflect the spacecraft moving into a new region, or it might reflect the region itself shifting because of a solar pressure wave. To separate these possibilities, researchers must compare multiple instruments, timing, solar wind propagation models, and the broader history of solar activity. Voyager therefore forced heliophysics to become more time-dependent. A static snapshot was no longer enough. The boundary had to be modeled as a moving system, influenced by delayed solar forcing and uncertain interstellar conditions. This is where the subject becomes deeply elegant, because the outer heliosphere is governed by equations of conservation, but the solutions are not simple. Mass, momentum, and energy must be conserved across shocks and flows. Magnetic fields exert pressure and tension. Charged particles diffuse and drift. Neutral atoms move differently from ions because they do not feel magnetic fields until ionized or transformed by charge exchange. Cosmic rays contribute pressure of their own. The heliopause is the place where all these ingredients meet, not as a fixed surface, but as an evolving solution to a difficult physical problem. Voyager did not give humanity the full solution, but it gave the first boundary conditions from inside the problem itself. It placed instruments where the equations touch reality. The breathing edge also changes the emotional scale of the Voyager mission. These spacecraft are not just drifting through dead emptiness. They are still near a restless border, close enough to detect delayed tremors from the star that launched them into light. Imagine a solar storm erupting when Voyager is already far beyond the planets. The storm expands outward, grows old, spreads thin, and years later reaches the heliopause, where it shakes the boundary and sends a wave into interstellar plasma. Voyager, almost impossibly far away, feels the electrons around it begin to oscillate. Then a signal travels back to Earth, taking many hours to arrive, carrying a faint record of a conversation between the Sun and the galaxy. That chain of cause and effect is almost too large for ordinary intuition, yet it is real. It tells us that the solar system has a pulse, not in the mystical sense, but in the physical one. Its outer edge responds to pressure, carries memory, and trembles under the long reach of solar storms. This discovery is one of the reasons the phrase "leaving the solar system" can be misleading if used too casually. Voyager crossed the heliopause, but it did not enter a realm where the Sun has no relevance at all. It entered interstellar space near the Sun, a borderland still shaped by the recent behavior of our star. The galaxy dominates the plasma environment beyond the heliopause, but the Sun can still disturb that environment with traveling waves. Inside and outside remain connected through physics. The boundary separates regimes, not realities. And this is perhaps the most beautiful truth Voyager found at the edge. The solar system fades outward by degrees, and even after the wind is stopped, the echo continues. The edge breathes because the Sun varies. It trembles because plasma can carry waves. It shifts because pressure balance is dynamic. It changes because the galaxy surrounding it is not a perfect stillness. And as Voyager listened to those faint oscillations beyond the heliopause, it revealed that our cosmic home is not a hard sphere floating in empty night, but a living bubble of charged matter, expanding, contracting, ringing, and adjusting as it moves through the thin sea between stars. The final question, then, is no longer simply where the solar system ends, but what Voyager's discoveries mean for us, for Earth, for future exploration, and for the way we understand our small, protected island inside the Milky Way. What Voyager truly tells us about where the solar system ends is that endings in space are rarely simple. And the deeper we look, the more the universe resists the clean borders our minds prefer. Before Voyager, it was tempting to speak of the solar system as though it were a nested arrangement of objects. The sun at the center, planets in orbit, icy worlds beyond Neptune, and then some distant darkness where everything belonging to the sun quietly stopped. But Voyager changed that picture by showing that one of the most meaningful edges of our cosmic home is not defined by planets at all, and not even by the farthest bodies that may still be gravitationally bound to the sun, but by plasma, magnetic fields, energetic particles, pressure, and motion. It taught us that the solar system has more than one boundary, each belonging to a different kind of physics. Neptune marks the outer realm of the major planets. The Kuiper Belt marks a broad population of icy bodies beyond the giant worlds. The Oort cloud, if current models describe it correctly, may represent the distant gravitational reservoir of long-period comets, stretching so far outward that Voyager will not reach its inner regions for hundreds of years. But the heliopause, the boundary Voyager actually crossed, is the edge of the heliosphere, the edge of the sun's wind, the place where the solar plasma environment gives way to the local interstellar medium. That distinction is not a small technical correction. It is the heart of the discovery. Voyager did not leave every possible meaning of the solar system behind, but it did leave the sun's protective plasma bubble, and in doing so, it became the first messenger to measure the space between stars directly from outside the solar wind. The answer it brought back was not a single location, not a number that can be placed neatly on a wall, but a layered story. The termination shock showed where the solar wind slowed from its long outward rush. The heliosheath revealed a disturbed outer sea of heated, compressed solar plasma, filled with turbulence, pickup ions, changing particle intensities, and magnetic complexity. The magnetic highway suggested that the boundary region could open pathways for particles, allowing solar particles to leak outward and galactic particles to enter inward before the final crossing. The heliopause itself showed the decisive shift. Heliospheric particles fell away, galactic cosmic rays rose, and the plasma density beyond the boundary matched the local interstellar medium. Cosmic rays proved that the heliosphere is not just a shape, but a shield, a vast electromagnetic filter that softens part of the galaxy's high-energy radiation before it reaches the planets. Plasma waves proved that interstellar space is not empty, but thinly filled with charged matter capable of ringing, carrying waves, and revealing its density through faint oscillations. Solar-driven disturbances beyond the heliopause proved that even after the solar wind stops dominating, the Sun can still send echoes into the nearby interstellar medium. Taken together, these discoveries say something more profound than Voyager crossed a line. They say the edge of the solar system is a dynamic boundary system, a magnetized shore where our star's influence fades by layers and the galaxy arrives through pressure, particles, and waves. This is why the Voyager crossings were so important for science. They forced models to become more honest. Before direct measurement, scientists had built impressive theories using magnetohydrodynamics, particle transport equations, pressure balance, and indirect observations of interstellar gas. Those models were not failures. Many of their broad predictions were right. There was a termination shock. There was a heliosheath. There was a heliopause. There was stronger cosmic ray intensity beyond the Sun's bubble. But Voyager showed that the details were richer than the early maps allowed. The boundaries moved. The distances differed by direction and time. The magnetic field did not behave with the dramatic simplicity some expected. The heliosheath was not a smooth waiting room before interstellar space. Particle behavior changed in stages, and the outer heliosphere carried the memory of solar activity years after events had occurred near the Sun. In science, this is one of the most valuable kinds of correction, not the destruction of a theory, but the refinement of it. Voyager did not tell us that physics was wrong. It told us that nature was using all of the physics at once. Pressure balance alone was not enough. Geometry alone was not enough. A static bubble was not enough. To understand the edge, scientists had to include time, turbulence, magnetic draping, particle diffusion, charge exchange, solar cycle forcing, and the imperfectly known structure of the local interstellar medium. The edge of the solar system became less like a drawing and more like a living equation, constantly solved by the Sun and the galaxy together. And for Earth, that realization has a quiet emotional weight. We live deep inside this structure without noticing it. We wake beneath blue air, weather, clouds, and daylight, protected first by Earth's atmosphere, then by Earth's magnetic field, and farther out by the heliosphere itself. The Sun is often imagined only as a source of heat and brightness, but Voyager showed it is also the maker of a vast magnetic shelter, one that surrounds the planets and reduces part of the cosmic radiation arriving from beyond. This does not mean the heliosphere makes life possible by itself, and it does not mean cosmic rays are the single key to climate, evolution, or habitability. Those questions are complex and should be handled with care. But it does mean our planet sits within a layered system of protection, and one of those layers extends far beyond the last planet. The Sun is not just overhead, it is around us, in a physical sense, through the wind and field it sends outward into the dark. Outside that bubble, the galaxy is more direct. Cosmic rays are stronger. Plasma belongs to the interstellar environment. Magnetic fields are part of the Milky Way's local structure. Voyager crossed into that realm and measured it, not as a mythic beyond, but as a real medium with density, waves, pressure, and radiation. That matters for the future too. Any spacecraft designed to travel far beyond the heliopause will move into an environment Voyager has only begun to characterize. It will face stronger galactic cosmic rays, faint but real interstellar plasma, dust and neutral atoms, magnetic fields, and disturbances that may come not only from the Sun, but from the wider galactic neighborhood. The distances involved remain almost beyond human instinct. Voyager is interstellar in the heliophysical sense, yet it is nowhere near another star. At its current speed, a journey to even the nearest stellar neighborhood would take tens of thousands of years. That fact does not diminish the mission. It places it in the proper scale. Voyager is not a starship crossing the galaxy. It is the first needlepoint measurement beyond the Sun's bubble, the first proof that a human-made object can survive long enough to touch the outer skin of our star's influence and send back data from the other side. Its greatness lies not in conquest, but in contact. It reached a place that had existed only as theory and made it measurable. And perhaps the most beautiful thing Voyager tells us is that the solar system does not end in silence. It fades into relationship. The Sun pushes outward. The galaxy presses inward. Magnetic fields bend and drape. Particles scatter and stream. Waves pass through boundaries. The heliopause trembles. The outer heliosphere remembers storms. Interstellar plasma rings faintly when disturbed. The boundary is not a wall between home and nowhere. It is a meeting place between a star and its surroundings. That changes the way we imagine our place in the Milky Way. We are not floating in a sealed private room. We are inside a bubble moving through a larger sea, and that sea has weather, history, and structure of its own. Voyager made that visible without taking a picture. It used particle counters, magnetometers, plasma wave instruments, and patient engineering to show that invisible things can be mapped, and that the deepest borders may be known not by sight, but by changes in motion, density, pressure, and energy. One day, the Voyagers will fall silent. Their power will fade below what their instruments and transmitters need. Their signals will stop crossing the darkness back to Earth. But the spacecraft will keep moving, carrying their golden records into the long future, while the knowledge they returned remains behind with us. They told us that the edge of the solar system is farther and stranger than a simple diagram, that our star protects a region of space larger than the planetary orbits, that interstellar space is not empty, and that the boundary between the Sun and the galaxy is alive with subtle physics. So when we ask where the solar system ends, Voyager answers gently. It depends on what you mean by end. The planets end near Neptune. The icy outskirts continue beyond. The Sun's gravity reaches farther still, but the Sun's breath, the wind-filled bubble that shields and shapes the space around the planets, ends at the heliopause, where solar particles fade, cosmic rays strengthen, plasma grows denser, and the Milky Way begins to touch us directly. There, in a darkness no human eye can see, Voyager found not a final wall, but a shore, and beyond that shore, the quiet ocean between the stars.